James Webb's red dots have an answer. And it's not what you think right now. More than 1,000,000 miles from our planet, the James Webb Space Telescope is pointed at one of the most puzzling corners of the observable universe. Scattered across the oldest regions of space are tiny, glowing red points of light, objects that should not exist in such a developed state at such an early moment in cosmic time. When they first appeared in Webb's data, they seemed almost insignificant, just a few reddish specks hidden behind distant galaxies. But the more scientists examined them, the more those specks refused to make sense. They were too bright, too small, and far, far too old. Now, after years of careful analysis, astronomers believe they finally understand what lurks inside those little crimson dots. What they found isn't just an answer to a puzzle, it's the beginning of an entirely new set of problems. Hidden inside each one is a black hole wearing the perfect disguise, surrounded by gas spinning at hundreds of kilometers per second. And the answer doesn't simply close a chapter. It forces science to rewrite several others. When the first images from James Webb arrived, the scientific community was ready to celebrate. After more than 2 decades of engineering, planning, political battles, and budgetary delays, the telescope had finally unfolded its enormous golden mirror at a stable gravitational point nearly 1.5 million kilometers from Earth. Scientists were expecting breathtaking views of ancient galaxies, long-dead stars, and perhaps a handful of novelties that would keep researchers busy for years. And Webb delivered on all of that. But with one addition nobody quite anticipated. It wasn't large, it wasn't dramatic, it was just a scattering of tiny, deep red points hiding among the brilliant smears of more distant galaxies in the background of the universe. At first glance, nobody knew what to make of them. Astronomers are accustomed to dealing with noise in their instruments. Detectors can malfunction. Cosmic rays leave bright streaks across camera sensors. Heat, electronic interference, and errors in data processing can all produce false signals that look real but aren't. Every good scientist knows that extraordinary discoveries often begin as very ordinary mistakes. So when the red dots kept appearing in Webb's data, the first instinct was skepticism. Teams of researchers went back to the raw data. They compared readings from different instruments. They revisited the same patches of sky on separate occasions and looked for inconsistencies that would reveal the dots as technical artifacts. None appeared. The dots stayed exactly where they were, unchanging and consistent across multiple independent observations. They were real objects, and they were genuinely emitting light that Webb's mirror was collecting. Then came the detail that transformed the curiosity into a genuine mystery. Many of these compact red objects were completely absent from older images taken by the Hubble Space Telescope. This was not a minor oversight. Hubble had spent more than 30 years mapping some of the exact same regions of the sky, producing some of the most famous and scientifically rich astronomical images ever made. Researchers knew those fields in enormous detail, every galaxy cluster, every faint smudge of distant starlight, every unusual object that had ever attracted attention. Yet when they placed Webb's new observations side by side with Hubble's archive, the little red dots simply were not there. It was as though an entire population of cosmic objects had been standing in plain sight for decades, invisible behind a veil that only Webb could lift. This absence was revealing because Hubble was never a weak instrument. It had transformed humanity's understanding of the cosmos, discovered evidence for dark energy, and peered into corners of the universe that ground-based telescopes couldn't reach. If Hubble had failed to detect these objects, that failure wasn't due to a lack of sensitivity. It was due to a fundamental difference in what each telescope was designed to see. The objects were there. The light was arriving. But it was arriving in a form that Hubble could not adequately capture. To understand why, it helps to think carefully about how these two famous observatories differ. On the surface, they share an obvious family resemblance: Both orbit above Earth's atmosphere. Both use large mirrors to gather ancient light, and both have transformed our picture of the universe. But in terms of what they were built to see, they're almost opposites. Hubble was designed primarily to observe visible light, the narrow range of wavelengths the human eye can detect, along with a limited extension into ultraviolet and near-infrared. James Webb was built to see almost exclusively in infrared, with instruments optimized for detecting heat signatures and warm emission from objects that emit little or no visible radiation at all. Infrared is sometimes described simply as heat radiation, and while that's partially accurate, it tells only part of the story. In astronomy, infrared has a special additional significance. It can penetrate clouds of gas and dust that completely block visible light. It reveals young stars still embedded in their birth nebulae. And most importantly for the story of the little red dots, it captures light that has been dramatically stretched by the expansion of space itself. That stretching is one of the most counterintuitive consequences of living in an expanding universe. A useful way to picture it is to imagine a loaf of bread with raisins scattered through the dough. When you bake the bread, the dough expands. The raisins don't move through the dough. They're carried apart by the expansion of the dough itself. In our universe, space behaves similarly. It is expanding, and anything traveling through it gets gently carried along. Light is not immune to this effect. As a photon travels across expanding space, its wavelength stretches, colors shift. What started as blue or white light gradually moves toward red, and eventually into infrared wavelengths, invisible to the naked eye. The farther the source, the longer the light has been traveling, and the more dramatically it has been stretched by the time it arrives. By the time light from the most distant little red dots reached Webb's mirror, it had been transformed so thoroughly that it sat entirely in the infrared portion of the spectrum. Completely outside the range Hubble could effectively capture, but precisely where Webb was designed to look. This explains why Hubble missed them. The light from these objects was arriving at Hubble's location the entire time, but it had shifted beyond the wavelengths its instruments were built to handle. The moment Webb opened its infrared eyes on those same ancient fields of sky, a hidden population of compact, energetic sources suddenly emerged from the background. What had looked like empty space turned out to be crowded with objects, invisible to every instrument we'd ever pointed in that direction. And Webb's enormous mirror, 6.5 meters across, with over 6 times the light-collecting area of Hubble's, meant it could gather enough of those ancient stretched photons to study them in meaningful detail. As Webb continued its surveys, more red dots emerged across different regions of the sky. The more that appeared, the stranger the collective picture became. These weren't isolated anomalies. They were a population sharing similar properties and scattered throughout the most ancient parts of the observable universe. Their light was concentrated into extraordinarily compact points. A normal galaxy, even a small one, spreads its glow across a wide area. These objects looked almost like single stars, except they were billions of light years away and impossibly bright for anything that's small. The light seemed squeezed into a region that should have held only a fraction of the energy being detected. Scientists gave these objects a name, not because they had explained them, but because they needed something to call them. They were named little red dots. It's an almost comically plain label for something so cosmically significant, but it stuck. And underneath that simple name was a genuinely profound question. What could produce so much energy from such a tiny space so soon after the Big Bang? To understand why the timing mattered so much, remember that in astronomy, distance and time are the same thing. Light moves fast, but the universe is incomprehensibly large. When we observe the little red dots, we aren't seeing them as they are now. We are seeing them as they were when the universe was still in its infancy. A photograph taken not long after the Big Bang set everything in motion. The standard picture of the early universe describes a rough, chaotic construction site. The first stars were only just beginning to ignite. The earliest galaxies were expected to be small, messy, and still assembling themselves through collisions and streams of infalling gas. Finding bright, compact, energetic objects there was like arriving at a site that should hold nothing but scaffolding and raw materials, and discovering a fully furnished skyscraper standing in the middle of it. The most conservative explanation was tried first. Perhaps these were simply very distant, ordinary galaxies whose light had been stretched by cosmic expansion. That's a real and well-understood effect, and it made sense to check whether it could account for everything unusual. It couldn't. The brightness was too extreme for the apparent size. The compactness was unlike anything seen in ordinary distant galaxies. The energy output exceeded what a young galaxy's stars could comfortably produce. And instead of a handful of unusual cases that might be dismissed as exceptional circumstances, Webb kept finding them everywhere it looked. Something different was going on. The next candidate explanation required asking what kinds of objects are capable of producing enormous amounts of energy from very small regions. That list is short, and one entry stands above all others: a black hole actively consuming surrounding matter. A black hole itself is dark. Nothing escapes beyond the event horizon, but the environment around a feeding black hole is a completely different story. Gas and dust falling toward it doesn't drop straight in like water down a drain. It forms a rotating disk, spiraling inward while different layers move at different speeds. The friction between those layers heats the material to millions of degrees, causing it to radiate intensely across a wide range of wavelengths. Under the right conditions, a single actively feeding black hole can outshine an entire galaxy of billions of stars, and it does so from a region that, in cosmic terms, is incredibly compact, sometimes no larger than our solar system. This could explain the tiny appearance of the red dots. Instead of requiring an impossible number of stars packed into an impossibly small region, the brightness could originate from a single powerful engine. But a hypothesis is not a proof. To confirm that black holes were involved, astronomers needed to find specific signatures written into the light itself. They found one in the spectral lines. When hot gas near a black hole releases energy, it creates distinctive patterns of light at precise wavelengths called emission lines, which act like fingerprints. Under ordinary conditions, these lines are narrow, but when gas is moving at extreme speed, which it does when orbiting something with enormous gravitational pull, those lines broaden. Some gas moves toward us, shifting its contribution to shorter wavelengths. Other gas moves away, pulling its portion longer. The combined result is a smeared, widened line that tells astronomers the gas is racing at tremendous velocities. In several of the little red dots, exactly this broadening appeared. The gas wasn't drifting through a quiet system. It was tearing around a central mass at hundreds or even thousands of kilometers per second. That kind of motion doesn't come from a cluster of stars. It comes from a gravitational engine of extraordinary mass. The black hole interpretation was becoming hard to argue against. The compact emission, the extreme gas velocities, and the sheer energy output all pointed toward actively feeding supermassive black holes buried inside these ancient, distant systems. In the modern universe, objects like this are well known. The most luminous among them are quasars, among the brightest objects in the observable universe, visible from billions of light years away because of the ferocious energy released by gas spiraling into supermassive black holes. The little red dots appeared to be earlier, denser versions of the same machinery, operating when the universe was only a few 100 million years old. But something didn't add up. Feeding black holes are normally loud. They produce X-rays, ultraviolet radiation, and sometimes powerful jets of material blasting out along their poles. X-rays in particular are one of the most reliable indicators that an active black hole is nearby. Astronomers have used X-ray observatories for decades to catalog active black holes across the universe. When they searched the little red dots for this expected signature, most objects were almost completely silent. Some produced faint traces. Many produced nothing detectable at all. An object that behaved in every other way like a feeding black hole was somehow failing to produce one of its loudest and most familiar signals. This inconsistency threatened to undo the entire explanation. Had the black hole interpretation been wrong? Could some unusual population of stars explain everything? Scientists went back and forth, but no alternative could simultaneously account for all the observations. The energy was too concentrated. The gas was moving too fast. The emission was too bright for the apparent size. Stars alone couldn't do it. The black hole idea was almost certainly correct, but something was hiding the evidence. That something turned out to be gas, not just any gas, a thick, dense cocoon of hydrogen wrapped tightly around the central engine, dense enough to absorb a significant portion of the radiation, trying to escape. To understand this, imagine placing a powerful furnace inside a room with walls made of meter-thick concrete. The furnace blazes at full capacity, but most of its radiation can't penetrate those walls. The outer surface glows faintly with warmth, but the intense energy stays trapped inside. The early universe was extraordinarily well stocked with hydrogen, the simplest and most abundant element in existence. Around some growing black holes, this gas may have accumulated into enormous, dense envelopes, not thin wisps but massive structures packed tightly around the central feeding zone. As the black hole consumed material and heated the surrounding disk, the resulting X-rays and ultraviolet radiation slammed into the cocoon rather than escaping into space. The cocoon absorbed the energy and re-emitted it at longer, less energetic wavelengths, primarily in infrared. Webb was therefore not detecting the black hole itself, or even the direct radiation from its disk, but the warm infrared glow of the surrounding cocoon. The outer shell was acting like a thick blanket, absorbing the intense inner radiation and releasing it as gentler heat that Webb could detect from billions of light years away. This beautifully explained both the brightness and the missing X-rays. The energy was real and enormous, but it was being filtered and transformed before it could escape. The compact appearance made sense too. Even though the cocoon could be physically large, all the action originated near a single central point, and from billions of light years away, the entire structure collapsed into one tiny red dot. The black holes weren't quiet. They were screaming into a soundproof room. This also answered a longer-standing question. Why had nobody found these objects before Webb? Traditional searches for active black holes rely on X-rays, ultraviolet emission, and visible light. If the cocoons blocked all of those signals, the objects would have slipped past every traditional detection method. They weren't truly invisible. They were wearing a disguise that earlier telescopes weren't equipped to see through. Webb's infrared sensitivity allowed it to detect the heat leaking through the outer shell of the cocoon, exactly the kind of signal that previous instruments had missed. But while the cocoon model solved the detection mystery, it opened a far more disturbing problem. If these really were supermassive black holes, they were already enormous at a time when they shouldn't have had nearly enough time to grow that large. The masses implied by the brightness and gas velocities ranged from hundreds of thousands to millions of times the mass of the Sun. In the modern universe, black holes at that scale aren't unusual. They sit at the centers of large galaxies that have had billions of years to develop. But finding them when the universe was only a few 100 million years old is an entirely different matter. Standard models of black hole formation begin with a seed. A massive star reaches the end of its fuel supply and collapses under its own gravity, producing a black hole with a mass of perhaps 10 to 100 times that of the Sun. This seed then begins to grow, pulling in surrounding gas, swallowing other black holes during galaxy mergers, and slowly accumulating mass over time. The process is constrained by a fundamental physical limit called the Eddington limit. The radiation produced by infalling gas pushes back against incoming material, and this outward pressure sets a natural ceiling on how quickly a black hole can accumulate mass under ordinary conditions. Even growing at the maximum permitted rate from a small stellar remnant, reaching millions of solar masses requires a very long time. The early universe had not provided that time. When researchers ran the numbers, the arithmetic became uncomfortable. Some black holes inside the little red dots were so massive for their age that they couldn't have formed from small seeds growing at normal rates. To reach their apparent sizes within the available time, they would need to have fed nearly continuously at the Eddington limit from the very moment they formed, with no interruptions and no shortage of fuel. Even then, for the most extreme cases, the standard model struggled. This left astronomers with two main possibilities. The first is that the early universe enabled black holes to grow faster than ordinary physics suggests. In the young cosmos, matter was packed more densely and gas was more abundant. If a dense cocoon surrounded an early black hole, that cocoon might have done more than hide the X-rays. It might have also helped the black hole grow by trapping the radiation that would otherwise push incoming fuel away. With radiation locked inside the surrounding material, the black hole could have consumed gas at rates exceeding the Eddington limit, a scenario called super Eddington accretion. Computer simulations suggest that brief bursts of this extreme behavior are physically possible. The challenge is sustaining it long enough and starting it early enough to explain what Webb is observing. The second possibility is more radical. Perhaps some of these black holes never went through a small seed phase at all. Instead of forming from a collapsed star, a black hole might emerge from the direct collapse of an enormous cloud of primordial gas. In the early universe, vast reservoirs of hydrogen existed before stars had formed. In rare places, gravity might have pulled one of these clouds together faster than it could fragment into individual stars. If the cloud remained hot and smooth enough to collapse as a single entity, the entire mass could fall inward and produce a black hole weighing tens of thousands or hundreds of thousands of solar masses from the very start. This process is called direct collapse, and it would produce what cosmologists call a heavy seed, a black hole that begins life already partway up the mass ladder, needing far fewer doublings to reach the sizes Webb appears to be observing. Direct collapse isn't a new idea. It was proposed partly to explain a handful of extremely massive early quasars that had already strained standard models, but Webb has dramatically expanded the scale of the problem. Instead of a few exceptional cases, there's now an entire population of compact, apparently overmassive objects scattered throughout the early universe. If even a fraction of them formed through direct collapse, the process may be far more common than scientists had previously imagined. The theory is supported by simulations, but the observations that would confirm it directly haven't yet been made. The little red dots may represent the outcomes of such events, but they show the aftermath rather than the moment of formation itself. What has been observed is a relationship, or more precisely, a broken relationship. In the modern universe, there's a well-established correlation between the mass of a galaxy's central black hole and the overall size of the galaxy itself. Large galaxies host large black holes. Small galaxies host smaller ones. The two appear to grow together over cosmic time, maintaining a consistent mass ratio, as if the same processes that shape one inevitably influence the other. The little red dots appear to violate this relationship. In many cases, the black hole seems far more massive than the visible galaxy around it would predict. The stellar content of the surrounding system is faint and underdeveloped, while the central engine is already enormous. It's as if someone installed the engine of an ocean liner inside a wooden rowboat, powerful enough for something vastly larger than the vessel surrounding it. This mismatch suggests that in some early systems, the black hole grew before the galaxy did, rather than alongside it. The traditional picture of galaxy formation assumes that stars build a large galaxy first, and the central black hole quietly follows. The picture that Webb seems to be suggesting is almost reversed. The black hole arrives first, and the galaxy grows up around it. Its radiation and powerful outflows could have heated nearby gas, disrupting some star formation while channeling material toward other regions. The black hole would be not merely a passenger in its galaxy, but an active architect, shaping the structure around it from the beginning. The monster may have preceded the city rather than the city housing the monster. There's another dimension to this story that becomes clear when astronomers consider what happened to these objects over time. The little red dots appear in abundance during a specific era of cosmic history, when the universe is only a few 100 million to perhaps 1 billion years old. Later, they become increasingly rare. This doesn't mean they vanished. It may mean they evolved. As the black holes consumed more and more gas, they also gradually depleted the dense cocoons surrounding them. Radiation and powerful winds slowly cleared the surrounding material. The thick hydrogen blanket thinned. Openings appeared, allowing X-rays and ultraviolet light to start leaking through, first as narrow beams, then in ever greater quantity. The object that had been a quiet little red dot would gradually transform into an active galactic nucleus, a blazing, recognizable engine of the kind astronomers have been studying since the mid-20th century. The transformation wouldn't be sudden. It would unfold slowly, like morning fog burning off under sunlight. But the end result would be a familiar type of object, now exposed and recognizable, having shed the disguise it wore during its earliest and most violent phase of growth. Evidence for exactly this kind of transition was found in a single object that stood out from the rest of the little red dot population. While most remained quiet in X-rays, this one was producing a detectable signal, faint compared with a fully exposed quasar, but unmistakably real. It appeared to be caught in the act of transformation, its cocoon still largely intact, but beginning to develop cracks through which higher energy radiation could escape. For researchers, this single detection was enormously valuable. It suggested the cocoon model wasn't merely an elegant theoretical explanation, there was direct evidence that the predicted transition was actually occurring. If this evolutionary picture is correct, then the little red dots aren't a separate class of exotic permanent objects. They're a developmental stage, something every major supermassive black hole may have passed through during the early universe, before growing large enough to clear its surroundings and announce its presence. They are not oddities, they are ancestors. That realization connects the distant early universe to something much closer to home. The Milky Way has a supermassive black hole at its center called Sagittarius A, weighing roughly 4 million times the mass of the Sun. Today it's remarkably quiet, feeding only sporadically and producing relatively little output compared with the violent monsters Webb is detecting in the ancient universe. But it wasn't always this way. In the distant past, when the Milky Way was young and still assembling its stars, Sagittarius A was almost certainly far more active. It may well have been surrounded by exactly the kind of dense hydrogen cocoon that the little red dots contain, feeding voraciously, growing rapidly, and shining in infrared wavelengths nearly identical to what Webb is now observing in the early universe. In a very real sense, what Webb is showing us in those tiny crimson points might be a portrait of our own galactic past. Long before the Milky Way developed its graceful spiral arms, before the Sun existed, before Earth formed, the black hole at our galaxy's center may have looked exactly like one of those little red dots, blazing with hidden energy, wrapped in ancient gas, invisible to any hypothetical telescope that might have been looking in this direction at the time. Webb may be showing us what home looked like more than 13 billion years ago. All of this raises a broader and somewhat unsettling question about our cosmological models. The standard model of structure formation has been extraordinarily successful. It predicted the large-scale distribution of galaxies, the cosmic microwave background, the primordial abundances of elements, and the existence of dark matter halos within which galaxies assembled. It is one of the most thoroughly tested frameworks in all of science. But the little red dots are placing pressure on it in ways that are difficult to dismiss. The problem isn't one single impossible observation. It's the accumulation of multiple pieces of evidence suggesting that the early universe was more developed, more active, and more capable of producing massive structures than current models comfortably allow. Black holes with millions of solar masses already present within the first few 100 million years. Compact, energetic sources that appear more massive than the galaxies surrounding them. An entire hidden population of objects waiting, undetected, for a telescope with the right kind of vision to reveal them. None of these observations individually breaks the standard model beyond repair. Together, however, they suggest something important is missing from our picture of the universe's earliest chapters. What might be missing remains an open question. The seeds for black holes may have been systematically larger than ordinary stellar collapse produces. Growth rates in the early universe may have briefly exceeded what standard physics allows under ordinary conditions. The feedback between early black holes and their surrounding gas may work differently than current simulations assume. Or there may be physics operating in the very early universe that hasn't yet been incorporated into existing frameworks. Processes that left no obvious traces in later cosmic history, but had dramatic effects when everything was denser, hotter, and younger. None of these possibilities is unfounded speculation. Each has theoretical motivation and at least some observational support. But each also requires more evidence before it can be elevated from a plausible hypothesis to an accepted conclusion. Great telescopes have always forced exactly this kind of reckoning. Galileo's crude instrument revealed mountains on the moon and moons orbiting Jupiter, disrupting centuries of philosophical certainty about the special and unchanging nature of celestial bodies. Edwin Hubble's observations showed that the spiral nebulae were independent galaxies vastly larger and more distant than anyone had imagined, expanding a universe previously thought to end at the Milky Way's boundary into something almost incomprehensibly vast. Webb is now doing the same thing at an even earlier and deeper level, revealing that the universe's first structures formed sooner, grew faster, and passed through phases that our previous generation of instruments simply could not access. The little red dots are not the end of a story. They are the beginning of a new chapter in one of the oldest questions humanity has ever asked. How did the universe we live in come to look the way it does? The answer is clearly more complicated, more violent, and more surprising than we thought. And the fact that it took photons more than 13 billion years to deliver this message, crossing almost the entire span of observable space and time just to land on a golden mirror floating silently in the darkness between Earth and the Sun, makes the discovery feel like something more than a scientific result. It feels like correspondence from another era. The universe sending a message written in infrared light, carried across an unimaginable distance, finally arriving at the instruments of a civilization just beginning to learn how to read it. The little red dots are telling us something about where everything came from. We are still working out exactly what that something is. But the fact that we can now ask the question precisely, rigorously, and with data rather than speculation is itself one of the most remarkable achievements in the history of human curiosity. And if a handful of faint crimson specks, invisible to every instrument we built before this decade, can reshape our understanding of the cosmos so profoundly, then the universe almost certainly has more such messages waiting. buried in wavelengths we haven't yet learned to read, hidden in eras we can barely reach, encoded in objects that will look just as insignificant as those first little red dots did, right up until the moment we finally understand what we are actually looking at.